Now we're going to define some terms that we'll frequently use throughout this class to describe the shapes of distributions of quantitative variables. So we like the idea of sketching a histogram or a density curve because it gives us an overall sense of how the data is distributed, if there's any interesting trends, if there's symmetry or not. And we'll have some actual vocabulary we can use that helps describe the shape of the distributions. One of those terms relates to what are called modes. The other one relates to what's called skewness. And we've already actually talked a little bit about outliers when we talked about box plots and violin plots in the previous video. Outliers are really defined arbitrarily in the sense that it's very data context dependent to decide what's outlier or unusual to observe in your data. But one starting definition is to say any data that's further than 1.5 times your interquartile range could be, from your extreme quartiles, could be considered outliers. And so that's what we do when we plot box plots. But again, it's really up to you as the data scientist to determine the context and what you would consider an outlier. Modes are going to give us a sense of basically the maximums, or both global and local, in a given distribution. So both of these plots here, because we have histograms, are plotting quantitative data, in which case a mode is either a local or a global max. If you have just one global max here, it's going to be called a unimodal distribution. If you have more than one, if you have two, it's called bimodal, and more than two, we typically call it multimodal. Now, there is a little bit of an interesting challenge in the sense that depending on how you choose your bin sizes, you could end up with just random noise and not necessarily a real true mode. But that's something that you can address as you basically play around with bin sizes, as well as play around with your density curve, or play around with different parameters that go into both of those, and until you converge on a general shape that looks like it's less due to noise and more due to the trends in the data. We will talk more in this course about how to try to assess noise versus trends, but in general, a histogram plot and playing around with the bins is a good starting point. For discrete or categorical data, we don't have the idea of multimodal. We just say the mode's the most commonly occurring value. All right, we also have this idea of what's called skew. And in this case, it's capturing if one tail of the distribution is longer than the other. That's at least how we're going to think of it in this class. And for our purposes, we're going to have kind of a simplified description. Distribution with a long right tail is what we're calling skewed right or positively skewed. Most of the time, that means that the mean or the average is going to be to the right of your median. In contrast, a long left tail is skewed left or negatively skewed, and then your mean's typically to the left of the median. There are always counterexamples. You can come up with kind of crazy multimodal distributions that break this idea, but for our purposes, that's generally what we're going to be looking for. And in terms of checking this in terms of a box plot, what you're looking for is where your median lies in relationship to your 25th percentile and 75th percentile. If it's right in the middle here, that's typically going to be symmetric. I'm also going to check what the tails, like the whiskers, look like here. Here you see that the median's shifted more towards the 25th percentile than the 75th, and that's typically going to be indicative that it's skewed right. Again, you'd also want to be looking for what's happening with the whiskers, but here that's consistent with a right skew. And this one here where you have the median closer to the 75th percentile and no real general trend in the whiskers either way is then telling me I'm likely going to be skewed left. There is actually multiple statistical definitions of skew where you can calculate an actual number, and In this class, we won't be diving into those, but you're welcome to look into them. And yes, when you get a positive number, it would correspond, at least this distribution would end up with a positively numbered skew. This one would end up with a negative. So it is consistent with the descriptions we're using. We're just not going to go to the level of detail of actually calculating a numerical value for this. All right, so far we've talked about three main ways that we can summarize the center of a set of data. And this is often a useful calculation we'll do when we're trying to describe a data set. So mean is what it sounds like. It's another word for the average. I take all of the values in the data set, add them up, and then divide by the total number. The median is your middle element of the data set when it's put in ascending order. And if you have an even number of data sets, our convention is going to just be to take the average of the middle two elements. You don't even have to worry about it because Python's going to do this for you behind the scenes. So you can just leave it at that. And then the mode is your local max or your global max for continuous data or quantitative data. And then for qualitative data, it'll just be your most commonly occurring value. Here, let's do a couple of practice questions about this. So here are two different distributions, and I want you to take a minute and figure out how you think the means of these distributions compare, how you think the medians of these compare. And if you say that they're different, tell me which one will be bigger. And a little caveat to this is you may be selecting more than one letter as part of your answer. All right, let's start with medians, because I want to basically split the area in half here. And so I can see the halfway point, because I have nice symmetry here. The area is split in half at 3 in both of these cases. So just moving these values, replacing the values 5 with instead 10, if I make a whole list of data points, is not going to change the middle value of all that data. And so the median here is equal on both of these plots. Now let's think about what's happening with the mean. So again, here I'm going to be adding up. Like 11% of the data is going to be 1s. That's a 1. Roughly 22% of the data are going to be 2s. Roughly 34% of the data are going to be 3s. So I'm going to be adding all those up and dividing by the total number. And due to the symmetry here, we can see that my mean is going to occur right in the middle as well. And you can try this with real numbers if you're not convinced. But what's going to change in my second distribution is instead of adding up, right, these values of 5 here, I'm going to shift and add up much larger values. I'm going to add values of 10. And so if you think about a mean, that's going to mean your numerator is now going to be bigger than what would have happened over here. Your denominator is still the same because you still have the same number of points. And so your mean is going to shift to the right. In this case, it doesn't shift too much. It's about 3.5 when you actually calculate it out. But it shifts slightly to the right because basically these larger values are pulling it in this direction. So we would have the mean of the distribution on the right is greater than the one on the left. Let's make some analogies to help us picture the mean in the context of physics. And so if you were to take this histogram, basically connect this with a rod, we could imagine cutting out cardboard that exactly were these rectangles and connecting them with a rod here and then trying to figure out the balance point where this would balance. And it's going to correspond actually to where the mean would be for the data. So you can think of mean that way as a balance point. The median, in contrast, is really the data point that separates the area under the curve from such that you have exactly the same amount of area on the right and the left. So I want the 50 percentile of the data, which means this area here is going to be 50% and this area here is going to be 50%. So this is going to be the median. It's exactly dividing the area in half. The mean, in this case, because I have a longer tail, I have more of these values. Even though it's a small number, I'm getting some larger values here compared to what I have happening on this left side of the distribution. And so these larger values here are going to be pulling the mean slightly to the right. Yes, so that's pointing out if the histogram's skewed. This is, again, I'm going to say typically. Again, you can always make a counterexample where that doesn't hold, but in a basic shape like this one, that's really what you can picture is happening. Okay, so for each of these, take a minute and I want you to label the median, the mean, and any modes. All right, let's start with modes on each of these. So this one's unimodal. This is my most popular, my most commonly occurring value here. I have two modes. I have my basically global max, my most commonly occurring value, but then I have another one here, the local max, where there's something interesting possibly happening. This one, again, I just have one mode, and here I can see three. Okay, so that's a good starting point. That's just looking for local or global max. Now let's look at medians. So median, again, is going to be I'm looking for the line here that's going to divide the area exactly in half, on the left and the right. And so this is going to be my median here. This one's going to be the median here. The median's exactly the same in both here. And the median's equal to this middle mode right here because of the symmetry. Okay, and then, well, yes, process of elimination, mean, but think about what's happening. I have a longer, this one's left skewed, so my mean's getting pulled over to the left away from the median. This one here, I have my mean's getting pulled over to the right because of some of this interesting information, like more of this data here is concentrated on this right side, as opposed to if I just had the tail go down and decrease like what I happened on this side. So that's going to pull the mean a little bit this way. Here they're all the same. And here they're also all the same. So, well, I would say we have three modes, but one of those modes is also the median and the mean. So you won't always be able to eyeball them at all. Like these are pretty basic distributions where I wanted you to have a good reference point. But when in doubt, you can calculate them numerically for our purposes. So that's an intro to some of the terms we'll be using to describe shapes of distributions.